Okay, and this is going to be video 2 for class on Thursday, November 6th. And we're going to continue with the second way that we're going to solve a one-way ANOVA. So another way that we might work on practicing solving a one-way analysis of variance is actually the way that we did it in class earlier, which is going to be looking at the raw data and calculating sums of squares and filling in our ANOVA table that way. Okay, so for this particular question, let's just do a variation on the one that we did in class. So for this one, our question is, does drug Y increase heart rate, which is measured beats per 20 seconds? And in this research question, we have 3 groups. We're going to have a placebo group with 5 individuals who are randomly assigned to that group, a 100 milligram group, and a 200 milligram group. And let's go ahead. I'm going to take you over here to our PDF hand file and scroll down. Let's begin to set this problem up in terms of hypotheses. So the first hypothesis that we're going to look at is our null hypothesis for ANOVAs. So let's look at notations and words. The notation for this hypothesis is going to be that the mean of group 1, the placebo group, is equal to the mean of group 2, the 100 milligram group is equal to the mean of group 3, 200 milligram group. So in words, I want that what we should do is make sure that we are naming our independent variables and dependent variables. So what that would look like is there is no difference in heart rate due to drug dose. Okay, so you can see that I'm saying there's no difference there, and I'm naming my dependent variable, heart rate, due to drug dose, which is going to be my independent variable. The alternative hypothesis for an F test or an ANOVA is always going to be this, that H sub 0 is false, or the null hypothesis is false. This is not true. Okay, so in words, that would be there is a difference in heart rate due to drug dose. All right, so my independent variable for this particular problem is going to be the dosage of drug Y, and the factors or the groups within that are going to be the placebo, the 100 milligram, and the 200 milligram. And your dependent variable is your heart rate. Now I just want to take a quick note and talk a little bit about something that has popped up on exams and that is can be a stickler for identifying the independent variable. So when you're trying to identify an independent variable, remember that the variable is never the subjects. So it's never the students. It's never the subject or the participant. It's never the women. What the independent variable is what's different between the groups of subjects. Okay, and so always ask yourself, what's different between the groups of subjects? That's your independent variable. All right, so let's go back to setting up a calculation for this. In order to solve this hypothesis, using raw data, I want to set up my worksheet the way that I've been setting up everything so far. So some of the things I'm going to need in order to calculate my analysis of variance, I'm going to need my sum of x for each of the groups, and I'm going to need my sum of x squared for each of the groups. I'm going to need to draw those numbers into my calculations later on. So I'm going to set up my worksheet much the way we've been setting it up so far. I'm going to get my raw score values for the placebo group, and I'm going to get my sum of x here. And then I'm going to get my x squared. So 23 squared is 529, 22 squared is 484. And I'm going to then sum those up to get my sum of x for my sum of x squared for my placebo group. All right, I'm going to do the same thing for the 100 milligram group, so the raw scores and the sum of x, and then I'm going to get their raw score squared and get the sum of x squared for the 100 milligram group here. And then I'm going to repeat the same process for my 200 milligram group, so the sum of x and then the sum of x squared for that group. Next, I'm going to go ahead and, because I'm going to need them later, as I've kind of put in the I don't know, jazzy signs here, that we're going to use these for post hoc. So I'm going to go ahead and calculate my group means, or the average beats per minute, or beats per 20 seconds in the 3 different groups. So I'm going to take, my sum of x for each of these and divide by 5, which is the number of people in that group. And so I get my mean scores for each of those groups. And there's going to be, not going to use those yet. We might not use them at all if the F statistic, F obtained is non-significant, but I'm going to have them there just in case. All right, so now that I have this information, I can begin working with my ANOVA source table and filling in my sums of squares, my degrees of freedom, my mean squares, and finally my F obtained. All right, so I'm going to switch back over here just for a second and pull up my ANOVA table. And I can you can see that I've begun to fill in the information here, and I'll show you how I calculated those in a moment. But we're going to get, this is called our source table, our ANOVA source table, and we're always going to fill this out so that we have source, between, within, total, and then we have our sums of squares, our degrees of freedom, our mean squares, and our F. Okay? So let's go back over to our worksheet and figure out, where did I get this sums of squares for between? Well, this is where I'm going to use my sums of squares between formula that we talked about in class. Let me scroll back up in my and look at this. So this was our formula for between groups variance, or our sums of squares between. So we can see that we're going to need our sum of x for each of our groups here, and we're going to need our number of subjects in each group here, and we're going to add those together for as many groups as we have, and then take that total and subtract the grand sum of x, which is, I'll show you how to do in a moment, divided by the total number of people overall in the experiment. So how does that translate to what we're working on? Let's go over to my worksheet here, okay, and give it a little look. So I'm going to start with the very top part here, the sums of squares between, and to calculate that, I basically I'm going to plug my numbers into my formula. Here's my formula stated again, okay? So I'm looking here for the sum of x sub 1. So that's going to be just the sum of the raw scores, okay, for group 1, which is 112. I'm going to take that and square that. So it's 112 squared, okay? And then the n is going to be the number in that group. So the number of raw scores in x that go into the sum of x are 1, 2, 3, 4, 5. So I divide that by 5. So I'm going to take the sum of x sub 1 squared and then divide that by 5. Then I'm going to add my second group, sum of x, which is 116. Okay, I'm going to square that and divide by 5, which is the number of raw scores in that group. And then because I have 3 groups, I'm going to do the sum of x for the third group, which is 130, square it and divide it by 5. So this is the number that goes inside these brackets. So you're going to do all of these orders first. So you're going to square 112 and then divide that by 5, and you should get 2,508.8. You're going to square 116, then divide that by 5, and you're going to get 2691.2. And then you're going to square 130, divide that by 5, and you get 3380. Once you've done that, you add all of those together, and that becomes the number at the beginning here. Okay, which should equal 8,580. So if you add these together, it should equal 8,580. Okay, then I'm going to need to subtract the grand sum of x squared over n. So this is this new kind of concept that we're doing with ANOVA. So the grand sum of x are just the sum of x plus the sum of x plus the sum of x. Okay, so the grand just means I'm going to total up all the sums of x's for my groups. And so what I'm going to do for the grand sum of x squared is I'm going to take 112 plus 116 plus 130. Or 112 plus 116 plus 130. And then once I add all of those together, the grand sum, then I square the grand sum. Okay, so it should be 358 and then squared, divided by big N, so the total number of people in the experiment. So that would be 5 plus 5 plus 5 is 15. So you can see, look, I'm just adding for the top, I'm just adding this plus this plus this and squaring that total, and then dividing it by this plus this plus this, 15. So when I did the calculations for that, this figure right here should equal 8,544.27. Go ahead and do that math and make sure you're getting it so that you can add it up. And so I'm going to take this total, which we decided is 8,580, and I'm going to subtract 8,544.27, and this is going to equal my sums of squares between of 35.73. So I've circled it in my worksheet, and now I can put that's my sums of squares between, and I can put that value here. So that, remember, is the variance in the groups between the groups, or the differences between the groups here. That's my treatment effect. All right. So now I can calculate my sums of squares within. And so if we go back to our formula, I'm going to show you from our previous notes. Our sums of squares within is a slightly different formula. So for this one, we start with the grand sum of x squared. All right? The grand sum of x squared. And then we're going to subtract the total value of the sum of x squared over n1 plus so on and so forth. All right. We have just worked with this value right here. It's actually this, with what goes inside these brackets, is the same as what we did with sums of square between. This number, though, is a new number. This number is a new number. So we're going to go ahead and then calculate our sums of squares within. Let me get back down to where we're going. Okay, so here I have put our formula for the sums of square within, the grand sum of x squared minus the sum of x squared over n for each of our groups. And remember, I just said this is the exact same as this in terms of the brackets. It's only that other piece of the formula that's a new number. So when I'm calculating that, you can see I have just transferred our 112, our sum of x squared over 5, our 116 squared over 5, our 130 squared over 5. This bracket's the same as this bracket, right? This new number, the grand sum of x squared, is a little bit different, okay? So for this one, we want to take each group's sum of x squared and add them together. So we're going to use our sum of x squared here for group 1, which is the 25.12. We're going to add that to the sum of x squared for group 2, which is 26.94, and then for 3, which is 33.90. So the grand sum of x squared is going to be the sum of x squared for each of the three groups added together. And so that value, once you do that, you should add those values together. You should get 8,596 as the first part of that equation, and then we're going to subtract this value, which we've already calculated, is 8,580. And so once you do that, you should get a sums of squares within of a 16. And we're going to then come over to our source table and put 16 in our sums of squares within. Okay. Now I want you to think about, how are you going to fill out your sums of square total? Right? Sums of squares total is going to be between plus within. So we're going to take 35.73 and add 16 to get our sums of squares total. Okay. Now let's go ahead and fill in our degrees of freedom for between, within, and total. To do that, we know that our degrees of freedom between is k minus 1, which is the number of groups minus 1. And so for this particular problem, we have three groups. We have placebo, we have 100 milligram, and we have 200 milligram. So k is equal to 3. So k minus 1 for between groups degrees of freedom is going to be 2. Okay. Within groups, variance, is going to be n minus k. So n being the big N, the total number of participants. So we start out with 15, and then we're going to subtract k, the number of groups, so 15 minus 3. So we should have 12 within groups degrees of freedom. And then to get the total degrees of freedom, we can add between to within to get our total. That's one way we can do it. So if we have 2 between groups, 12 within, we should have 2 plus 12 is 14 degrees of freedom total. But the other way, the clean way to do it, is we know our total degrees of freedom is big N minus 1, where big N is the total number of people, 5 plus 5 plus 5, which is 15, and then we subtract 1, which is 14. So either way should give you 14 total degrees of freedom. All right, now we can calculate our mean squares. So I'm going to go ahead and switch to this next one where I've filled in all of the correct values for you. To get our mean squares between, we just take our sums of squares divided by our degrees of freedom between. And so if you take 35.73 divided by 2, you should get a mean squares between of a 17.87. We can take our sums of squares within divided by degrees of freedom within in order to get our mean squares within. So that's going to be 16 divided by 12 should equal 1.33 for our mean squares within. And so now we can get our F obtained, our actual test of our hypothesis here. And so recall that F obtained is going to be over here. F obtained is going to equal mean squares between divided by mean squares within. So we take the 17.87 divided by the 1.33, and then we can fill in our F obtained here in our source table as a 13.44. All right. So at this point, in order to test our hypothesis, we have our F obtained. Now we need to figure out what's the critical region that we want to see is this number in it. So I've gone ahead and pulled together over on our worksheet over here a curve, an F curve. Remember, this is always going to be a positively skewed curve. It starts at 0, which is 0 variance, and then it's going to tail off into the positive numbers. So to find our critical F value, I have looked up on our F table, and let me go ahead and this would be an online example of an F table. So I want to look at an F table. I have 2 degrees of freedom between, and I have 12 degrees of freedom within. So I'm going to look at 2 and 12, and this particular table is going to tell me that 3.89 is my critical F value. Let me go back to where I want to be. Okay. And so I can see I have my critical F value that I have defined here. And so I can draw it on my curve and then shade in the tail. Now I just need to know where my F obtained is. And it's going to be way out here in the tail. So I've made a little star and labeled it. Is it in the shaded critical region in which I am going to reject the null hypothesis? Yes, it is. And so my decision then is going to be that I'm going to reject the null and accept the alternative. The alternative being that drug Y does affect heart rate. Now remember, right now I don't know yet how it affects it, but I do know that there's something going on there, that it affects it in some way. At this point, I can go ahead and look at my effect size calculation. So to calculate effect size in a one-way ANOVA, we want to use eta squared, which is this sort of stylized n squared. And it's a very simple calculation. The formula is the sums of squares between divided by the sums of squares total. So it's basically the variance between groups divided by the total variance in the equation. So I'm going to take 35.73 and divide it by 51.73. And I end up with a 0.69 as my effect size. Now let's go back up in our slideshow to our interpretation of eta squared, because it's a little bit different than Cohen's d. This is one of those new things you just need to memorize like you did for Cohen's d. So for eta squared, any value that's greater than or equal to 0.25 is considered a large effect size. So we're going to say that this is a large effect size. 0.69 is above a 0.25. Now in language, how do we say that? Okay, because eta squared tells us the proportion of variance that is explained in the dependent variable that is explained by the independent variable, we can make a very specific statement here. So I'm going to, in a sentence, I'm going to be able to say then that changes in the dose of drug Y, so changes in my independent variable, account for 69% of the variance in heart rate. Okay? All right, so I have this significant F-test. I have rejected my null hypothesis. I have said there is some difference, but now I need to do post hoc comparisons in order to determine what that difference is. And so let's go here to my worksheet where I have done the post hoc calculations. We're going to use Tukey's HSD, honestly significant difference, to figure out if our groups, which groups are significantly different from which. So for this, the equation for Tukey's honestly significant difference is Q times the square root of mean squares within over n. Remember, the rule is that n is the size of the cell, not total n, but the number of people in the groups that you're comparing. So that would be 5 in this case. So to find Q, I've gone to the back of the book and I have looked up what the critical Q value is for 2 and 12 degrees of freedom. Okay. And I've found that that number from the back of the book is a 3.08. So do take a moment and look in your back of the book, look in the back of your book and identify 3.08 and make sure you know how to get to that point. All right, then I'm just going to take the square root of our mean squares within, which from our source table is 1.33, and divide it by n, the number of people per cell, which is 5. So I'm going to take 1.33, divide that by 5, then take the square root, which equals 0.52, and now I can take 0.52 times my critical Q value, 3.08, and I end up with an honestly significant difference comparison value of a 1.59. So this is the comparison. So what I'm doing now is I'm going to say 1.59 is the lowest difference between any two groups that is significant. So I want to see, is the difference between the mean of group 1 and group 2 this equal to or larger than 1.59? Is the difference between group 1 and group 3 equal to or larger than 1.59? And is the difference between group 2 and group 3 equal to or greater than 1.59? I'm just looking for every possible comparison group and comparing it to that critical value of an honestly significant difference. And so let's look at this, what I've done here. So I've taken the comparison of the mean for group 1 minus the mean for group 2, absolute value. We're interested in sort of the absolute difference between them. So we're going to make it positive. So I take, remember way back up here, we calculated the means for each of these groups. Not that far. So we calculated the means, so I'm going to grab these numbers and compare them to Tukey's honestly significant difference. So I take the mean of group 1 minus the mean of group 2, and it equals 0.8. So I can compare that to 1.59. Is it equal to or greater than that? No, it is not. So that tells us that the heartbeats, the heart rate is not significantly different between people who got the placebo and people who got 100 milligrams. Okay? So then I can compare group 1, the mean of group 1, to the mean of group 2. So group 3. So the mean of group 1, subtract the mean of group 3. So 22.4 minus 26. That gives us, we're going to take the absolute value of that, so that gives us a value of 3.6, and I can compare it to 1.59. Is it equal to or greater than? Yes. So there is an honestly significant difference between those two groups. Then my final comparison is between group 2, the 100 milligram group, and group 3, the 200 milligram group. So I take the mean of group 2, subtract the mean of group 3, take the absolute value, and that gives me a 2.8, and I compare the 2.8 to the value of 1.59. Is it equal to or greater than that? Yes, it is. So that means there is an honestly significant difference between people who had 100 milligrams of the drug and 200 milligrams of the drug. All right. So the final thing that we want to look at in this particular problem then is how to report my results in APA style. So here's my report. The results of a one-way ANOVA indicate that drug Y significantly affects heart rate. F, with degrees of freedom 2 and 12, is equal to 13.44, comma, p-value is less than 0.05, comma, and my effect size, eta squared, is equal to 0.69. So I'm saying, here's the result of my F omnibus test first. And you're going to report it in that specific way. Then I'm going to follow it up and report on my honestly significant difference. So I do want to follow up and just say, well, okay, it does affect heart rate, but how? Tell me more about that. So that's what this second bit does. So I say Tukey's HSD post hoc comparisons showed that people who received a dose of 200 milligrams of the drug, and then I report the mean and the standard deviation of that particular group, had significantly higher heart rates than both the 100 milligram group, I report the mean and standard deviation, and the placebo control. So notice here I'm reporting that group 3 is significantly different from group 1 and group 2. And I'm reporting exactly how. I'm saying they had significantly higher heart rates because 26 is higher than 22.4. 26 is higher than 23.2. Then I'm finally reporting the non-significant difference between the 100 milligram group and the placebo group, this group right here, this comparison over here. So that the difference between the 100 milligram group and the placebo control was not significant. Notice I don't restate the means or standard deviations for these groups because they're already involved up here. Okay, I've already reported them. I don't need to report them twice.